to present my work titled Observing Nulls in the Primordial Correlations via the 21 centimeter signal. This is a work done in collaboration with my collaborators Dr. Shyam Balaji, Professor Shiv Sethi, Professor Joseph Silk, and Professor Sriram Kumar. It is available at this archive identifier. So, this is a bit of a deviation from the general theme of this day so far. I will be speaking more about early universe first compared to the late universe talks that have been discussed thus far. Towards that end, I will first introduce a bit about inflation and the generation of primordial perturbations, and then I will specifically focus about a class of models called ultra-slow roll models of inflation, which produces a unique feature of interest, namely the nulling of primordial correlations. I will then illustrate the feature generated using two representative models of interest. Then I will come to the important part of my talk where I connect the feature generated in the primordial perturbations with the 21 centimeter signal at the level of 2-point function as well as the 3-point function. Lastly, I will briefly touch about the error due to Poisson fluctuations associated with both the power and bispectra. Finally, I will conclude with a brief summary of results. So, just as a brief catch up, inflation is a successful paradigm that solves the horizon problem. Namely, it just makes sure the current universe is homogeneous, isotropic, and so on over large scales. And it also provides a natural origin for the perturbations that we observe across all observational scales. It has been depicted in a sort of cartoon on the left-hand side, where you see the left-hand side of this plot corresponds to the behavior of co-moving Hubble radius during inflation, and the right hand side corresponds to the standard lambda CDM, the hot Big Bang evolution of the co-moving Hubble radius. The perturbations and the scales corresponding have been depicted in co-moving wave numbers, co-moving wavelengths as horizontal lines here. We know that the large scales correspond to the CMB measurements, CMB observations, and the small scales have been gathering interest in the context of primordial black holes and secondary gravitational wave generation. We will be focusing particularly on the intermediate scales, which corresponds to the 21 centimeter signal and also to some extent to the spectral distortions associated with the CMB spectra. As we can see, all these scales evolved from deep inside the Hubble radius during inflation. So, any non-trivial physics that may happen during the inflationary epoch may get imprinted in these corresponding observables, and that can be constrained when they re-enter the Hubble radius and when we detect them in the late time somewhere sitting here. This is a nice illustrative plot that tries to convey what I am trying to say. This is taken from this reference given below, where we see the scalar power spectrum denoted as P zeta has been constrained by all these shaded regions corresponding to various observations. The dashed lines correspond to the upcoming observatories, particularly the GW observatories. But as you can see, over large scales, the CMB rules out a huge fraction of these primordial power spectra, and it is tightly constrained to be a nearly scale invariant spectrum. And we are trying to do a similar analysis for all subsequent smaller scales as well. So, what are these ultra slow roll models of inflation? These are special class of inflationary models that have garnered huge interest in the context of producing primordial black holes and secondary gravitational waves over small scales. They do this by enhancing scalar power over small scales, and it is well known and well studied in the literature. See, for example, these references given below. But what is less noticed is that before they produce these enhanced power spectra over small scales, they also produce a feature of null or a dip in the intermediate regime that may as well be corresponding to these 21 centimeter signals, particularly if they are placed suitably in this window of wave numbers. So, this is what we will explore in our talk. I will illustrate this using ultra slow roll models. This is the typical model that we will consider. The shape of the power, potential driving ultra slow roll inflation is illustrated here. As you can see, in both the red and blue lines, which correspond to different base models from which ultra slow roll is achieved, they contain an inflection point close to the end of inflation. So, as the field rolls down such a potential, it stagnates briefly, and this is best captured by this first slow roll parameter, namely epsilon 1, which is defined in terms of the Hubble parameter like this. And it is known that as the field undergoes this epoch of ultra slow roll, this epsilon 1 undergoes an exponential suppression, with this Q parameter being typically 6. These are just details of the model, and you can see elaborate discussions in the references given below. But I am trying to motivate what is the general characterizing feature of ultra slow roll models. So, with this, what we get, we see the corresponding features in power and bispectra. For completion, I will provide the expressions of power and bispectra, namely PS and BS, in terms of the RK, which is the scalar perturbation, mode function of the scalar perturbation in Fourier space. So we have these 2-point correlations computed, numerically evaluated, propagated across inflation in a given model of ultra slow roll inflation, and evaluated at eta e corresponding to end of inflation before we propagate it across and see the corresponding imprints in the standard lambda CDM picture. So I will just briefly illustrate the vanishing of these mode functions that may happen over specific wave numbers in this model of ultra slow roll, because the enhancement has been well studied, and I have illustrated that in this right hand side plot, where I have shown the evolution of the mode function itself in 3 different shades of green. This cyan region corresponds to the regime of ultra slow roll, and as you can see, a dark green mode, as it goes through the ultra slow roll regime, gets seriously enhanced in amplitude. And these are the scales that are known to produce primordial black holes or secondary gravitational waves on re-entry, but not the topic of our interest. The large scale modes which have exited the Hubble radius way before this ultra slow roll epoch, they propagate, and when they come across this ultra slow roll regime, what they undergo can be analytically captured in these 2 forms of the mode function solutions. I'm not going into the mathematical details, but I'll just say that there are 2 components to this superable evolution of the mode function. And what happens during slow roll is that the growing mode, which is the first term, dominates over the decaying mode. But during ultra slow roll, because of this inverse relation with respect to the eta, the conformal time, the decaying mode, the so-called decaying mode, starts dominating over the growing mode. So it is in some sense a role reversal between the growing and decaying modes. This happens for certain modes in such a way that the competition between the growing mode and decaying mode exactly cancel out each other, and the mode function can indeed vanish. And if we impose that condition that Rk vanishes for specific k called k dip, then we arrive at a condition on this k dip, the wave number that is going to vanish, in terms of these model parameters, namely k1, the wave number at the beginning of this ultra slow roll epoch, and delta n, which is the duration of ultra slow roll in e-fold. So armed with this, to know where exactly the nulling in power is going to occur, note that if the mode function vanishes, all the correlations that contain this mode function is also guaranteed to vanish. So we will understand the imprints on this on the power spectrum first. These are the 2 models that I will be illustrating my findings with. One is that simple toy model of that is proposed way early by Professor Starobinsky, called the Starobinsky model, and the other is a critical Higgs model which comes from a high energy physics motivation. For details of these models, you can refer to these original references, but here we just take these models. I fine tune the parameters such that I produce the dip of my interest at a regime which is between 10 power minus 1 to 10 megaparsec inverse, and I achieve that at 7.6 megaparsec inverse for both these models. This is the behavior of power spectrum. Of course, we can enhance power after the dip has been achieved, and that has separate implications of their own, but we will focus mainly on the dip that is achieved here. You can ask that this is just a dip and not an exact nulling of the power, but this is because of the choice of parameters that we have worked with. Note that there are constraints coming over large scales from CMB and constraints over this regime on the top from the spectral distortions. We are obeying all these constraints, and within those constraints, we find a suitable choice of parameters which produces us this dip. Having this dip at the power spectrum, we can proceed to compute the corresponding signal in the 21 centimeter, but we also compute the corresponding signal at the level of bispectrum. These are the 2 bispectra of the 2 models of interest. I have of course plotted them in certain limits, because bispectrum involves 3 different wave numbers, and I have plotted them in equilateral, squeezed and flattened limits, which are popular limits that are well known in the literature. And you can see this bispectrum has multiple other dips as well. This doesn't contain just the pure dip that I have been speaking about at 7.6 megaparsec inverse. But that is because of the very nature of the bispectrum and the integrals that get involved in the calculation. But without getting distracted about the other dips or other features, we will just focus on the dip around the 7.6, and we see that despite other dips, this dip is prominent and still be visible at the same wave number of interest. So this is a generic dip that is observed across higher order correlations as well. Now I will briefly try to connect to the 21 centimeter signals. This we have all been seeing from the morning, that this is a well-known expression of the global temperature difference, and we use the standard canonical values of the lambda CDM parameters such as omega b and so on, and we have specifically focused on 2 redshifts to compute our observables of interest, particularly 27 and 50. 27 taken in the context of the highest range of redshift that can be probed by SKA, and 50 is touted to be well within the range of future space-based mission that have been discussed in the previous session as well. So with these two motivations, we go on to look at the signals at the two specific redshifts. This is the P21, which is something like one of the crucial results of my talk. I see that the P21, when zoomed in around the wave numbers of my interest, I see that the dip is reproduced in both the models of interest, not so surprisingly. But just to compare and give a reference for what we should expect from a typical slow roll inflation and followed by a standard lambda CDM, I have plotted the two corresponding standard signals in dashed lines here as well. So we will see a marked difference in the amplitude at two different redshifts. Obviously, the redshift at 50, the signal at 50 will be stronger than signal at 27 because of the delta V behavior, but there will be a marked difference from the expected lambda CDM plus slow roll prediction. We also computed the corresponding Poisson fluctuations, which are presented in dotted lines, but those are much below than the signal that we expect at the level of power spectrum. So proceeding to the bispectrum, since we have the primordial bispectrum, we connected to the bispectrum of the 21 centimeter as well through this relation, and we capture the effects of baryonic perturbations as we all know through the transfer functions, and we see that the dip, apart from other dips that we already know are occurring at in the primordial bispectrum, there is a marked dip at the same K dip of 7.6 mega per second burst. So this dip truly is generic and can be observed even in the 21 centimeter signal at both the redshifts of 27 and 50, which have been plotted in solid and dashed lines. But one crucial difference compared to the previous plot is that unlike the Poisson fluctuations which are subdominant to the signal, the Poisson fluctuations associated with the bispectrum are dominant compared to the signal in both these models, of course. Now, what are these Poisson fluctuations? This brings me to the last part of my talk, the error due to Poisson fluctuations. We know that since these are discrete sources that are emanating the signals, and because of enhanced power, there may be larger probability of formation of halos. These Poisson fluctuations have to be taken into account consistently in our predictions, and that is what we have done. This P21 PF is the Poisson fluctuation associated with the 21 centimeter signal, and that is related to FC and N bar, where FC is the collapse fraction of the halos computed from standard pressure sector formalism, and N bar is the mean co-moving number density of halos. You see, there is no K dependence in this P21 apart from the delta TB and K cube. So we get a standard power spectrum associated with P21 PF. But B21 is slightly more complicated at the Poisson fluctuation level, in that it depends on 1 by n bar square as well as the power spectrum, the original power spectrum of the 21 centimeter signals. And because of that, we see that the bispectrum is dominated by the Poisson fluctuation errors compared to the power spectrum where it is subdominant. But an interesting feature to note is that because of this bispectrum, depending on the power spectrum of the original signal, we may still get to see the dip even in the error at the same location of K dip equal to 7.6 mega per second burst. So even though error dominates, the error may still contain the dip arising from the original model of ultra slow roll inflation. So this is an interesting signature that we found out, and we have put it out in archive in this identifier. And I will just briefly conclude with the summary of my results. What I have been trying to convey is that a brief epoch of ultra slow roll can lead to a null at a specific wave number called K dip. And this dip gets translated into a nulling of all the primordial correlations, namely the power spectra, bispectra, and so on. Such a dip, when captured in the wave number of interest, can be observed at the redshifts of redshift 27 and 50, which are well within the sensitivities of SKA and especially future lunar arrays and so on. Though the Poisson error dominates the 21 centimeter bispectrum, the behavior of error still contains the dip, which is an interesting signature of this ultra slow roll scenario. Observing such a dip in the 21 centimeter signal can open up a possibility in that the subsequent higher order wave numbers, can be probed for enhanced power, which can be observed in gravity wave missions and so on. So with this, I will thank you for your attention, and you can find the detailed analysis of my work in this paper.
Thank you, Ragavendra. So we have questions.
Have you compared the thermal noise induced sensitivity because at k of 10, I don't think any detections are possible.
No, we understand that, but this is not taking into account any of these astrophysical foregrounds or thermal noises. We are just focusing on the primordial signals. I'm just presenting the signals and the associated.
No, so to put my criticism in encouraging language, have you looked at this at much smaller scale, smaller redshifts in, for example, small scale structure measurements using Lyman alpha forest, where we will soon start measuring 3D quantities? There, this might be possible actually. So 21 centimeter might not be the best probe for this.
Yeah, so we tried to see how far we can have freedom in moving this feature of interest, particularly as you suggest to a smaller K. But we are severely constrained by the CMB constraints. These models already are in tension with the spectral index constraint that is coming from the Planck 2018. Okay.
Lyman alpha forest can get you to these K values.
Okay.
21 centimeter can't, is what I'm trying to say. So you might be interested in looking at this at the redshifts where Lyman alpha, because Lyman alpha forest is exquisite measurements at small scales.
Okay.
So that easily can get you to K of 10. This is co-moving megaparsec inverse, right?
Right.
Yeah, so then it should be possible for you to get to K of 10.
Okay, I will certainly look into that. But regarding this probing this high K, there has been criticism earlier also, and Professor Shiv Sethi had addressed this in the paper using some novel method to detect, particularly enhancing the sensitivities and pushing the wave number boundaries. I'm not completely comfortable with that, to be honest, but please refer to our work, which contains a specific discussion for achieving this K.
Yeah, thank you. Yeah.
Thank you.
Maybe one more question.
Yeah, this small this power spectrum feature at k equal to 7 megaparsec inverse, will that affect the structure formation, like formation of halos? Have you tried check that?
If you are thinking about sigma 8 measurements, this may
not sigma 8, but say mass function.
Right, that will definitely increase particularly this enhancement after the 7.6. There is an enhanced power, right? So it will increase the probability of forming large halos, and that is precisely what is coming in as the error due to Poisson fluctuation. As you can see, this N bar and FC, they have not been calculated for the standard power spectrum, but for our modified power spectrum. And modified power spectrum increases these probabilities.
Yeah, so if you have increased power spectrum, and that will increase the number of halos,
right?
And that will also, so you have more number of sources,
right?
So it will indirectly affect Lyman alpha photon production or X-ray photon production during the cosmic dawn.
Right.
So it has some indirect effect on the structure formation. So
okay, those indirect effects we have not explored as yet. For the moment, we just looked at the dip of interest, but certainly we will look into that.
Thank you.
Any other questions for Ragavendra? If not, what is one?
So Raghavendra, you consider the standard lambda CDM model, right?
Right.
In order to calculate your power spectrum. So what do you take for different cosmological models?
Oh, we did alter the subsequent evolutions. The only model that we had was for the inflationary part. The subsequent evolutions were for the standard cosmological background parameters, but with our power spectrum. That is
So that's if you take the different. My question is, if you take different power spectrum for different cosmological evolution, then what do you expect it will change in your work?
That is very hard to comment, because starting from omega b that enters in the delta TB calculation, we will have to rework everything, as in the subsequent evolution, the transfer function, and so on. You are suggesting to alter the subsequent evolution, right?
Yeah. So I am saying that, for example, if you do a lambda CDM model, if you take a warm dark matter model, some other thing, so power will again suppress, because lambda CDM model power spectrum is delta growth is large in particular scale, but that will again suppress because of dark matter properties.
Right. Then we will have added features.
Yeah.
That
so
I cannot readily comment on. That depends on the subsequent modeling as well. The additional model that you are introducing, that will have its own features. That I cannot.
Okay.
Thank you. And let's thank